Hello everyone. Till now we consider functional depending on function of single variable. The same concept can be extended to function of several variables. In this lesson we will derive Euler-LaGrange equation of two variable function z of x, y which represent a surface on 3D space. Thus, let us suppose capital F x, y, z, z of z sub x, z sub y, this one, be a function with continuous first and second derivatives with respect to all its argument, and consider the functional of the form that is given by j of j z is equals to double integral over the region R the functional times dx into dy. So this is our functional. As in one variable case, we are looking for 2D curves. Here we are looking for 3D surface z which follow the following condition, and that is that z of x, y and its first and second derivative are continuous in R. Z of x, y takes given value on the boundary that we represent by gamma of R, and a functional has an extremum for z is equals to z of x, y. The same necessary condition that variation of a functional vanishes identically applied in all cases. Thus, we find the variation of a functional and make it equals to 0. Before finding the variation, we will write a lemma which we will use in proving the Euler-LaGrange equation. The same as we learned before, we will not prove but we just state. You can find the proof in any calculus of variation book. The lemma goes like this, and that is alpha of x, y is a fixed function which is continuous in a region R, and this double integral over the region R alpha of x, y times h of x, y dx dy vanishes for all h of x, y which has a continuous first and second order derivative in R equals to 0 on boundary gamma of R. Then we say that alpha of x, y will equals to 0 everywhere in R. So if this integral is equals to 0 for every h of x, y which has a first order continuous and second order continuous in R, also the value of h of x, y in the boundary gamma of the R also equals to 0, then this integral implies that alpha of x, y is also equals to 0 in R. Now let us find the variation of a functional. Let h of x, y which is arbitrary function with continuous first and second order derivative in R and vanishes at the boundary gamma to satisfy the boundary condition. Suppose the increment in function is h of x, y, then the increment in the functional will given by delta j is equals to j of z plus h minus j of z, as we see in the first one variable case. Now I will put the value of j of z plus h, that is given by this following integral, and j of z which is given by this following integral. Now same as before, we will use the Taylor Theorem to write this difference as the following form, that is integral over the region R f sub z h plus f sub z x sub x h of x plus f z sub y h sub y dx dy plus some higher order term. We know that the variation is basically the linear term that is written here, so I will write the linear term is equals to del j, which is a variation. Now let us suppose the following term, that is double integral of r f z sub x hx plus f z y hy dx dy. What you can do here is just write the following term. The first term is as before. I add two terms. I first add the same term and subtract the same term. This will not affect my equation because you can simply cut them and this will become the following one, that is the same as before. But we will not do that. Now what we can do is to write this function and this function as the same as a multiple rule. We can write it as the double integral del by del x of the function f sub z x h, which is equals to, first we will differentiate the first function times the h, which is the following term, and the second term of this multiple rule will be this one. You can verify by differentiating the multiple rule, and this will, because this is as before. Now we use the Green's theorem, which is given by the following statement, that is the double integral of the function del q over del x minus del p over del y dx dy can be regarded as the line integral over the boundary p dx plus q dy. So we apply the Green theorem in a first term, and what we get is the line integral of fzx h d dx dy minus fzy h dx. But we know that h vanishes at the boundary gamma, so this term will be cancelled out and this become equals to 0. So what we get, we will put the value of the term, this term, on the variation, and what we get is that del j, which is a variation of functional, is equals to the double integral fz minus del over del x fzx minus del over del y fzy times h of x comma y dx dy. And by the lemma 1 that we learned before, this says that this function must be vanish for all value of h. So the following equation, we again obtain the Euler equation for several variable, for the two variable in this case. So in this way we can prove the Euler equation for two variables. We can generalize the same argument for n variables, but we will not do that here in this lesson, but in some other lesson. So that was all for today's lesson. What we will learn is how to derive the Euler-LaGrange equation for the two variable case, where we are finding a surface, extremum surface, that maximize or minimize the functional. So thanks for watching. If you like the video, you can like, share and subscribe so that you will not miss the further videos on calculus of variations.